Okay, in the final lesson of the first part of Unit 4, I'd like to talk about applications of composite and inverse functions. Many times we have two components that interact with one another to produce a final result, and often it's nice to have a single function built on a single variable that accounts for both of those components. In this particular scenario here, we've got the radius r is increasing with time, and we're talking about a volume of a balloon, by the way. This description goes with this problem. And the radius of the balloon, based on the time that's passed, is equal to this equation. So if I want to know what the radius of the balloon is at 10 seconds after it started inflating, well, I would plug in the number 10 here. If I wanted to know what the radius of the balloon was 12 seconds after we started, well, I would plug in the number 12, and so on. We're not going to find the surface area as indicated here with this expression. Instead, I want to go with the volume, since the volume formula is provided to us. So you'll notice down here that the volume of a sphere, or a spherical balloon, is dependent upon its radius, and that formula is 4/3 pi times radius cubed. But the radius of the balloon is dependent upon time, and the radius of the balloon will be 2/3 times t cubed. So the argument can be made, it would be certainly nice to have the volume of the balloon based on the amount of time that's passed, rather than having to compute two different results. And that's entirely possible because the volume of the balloon would be the result of the radius, or would be dependent upon the radius, and the radius, of course, is dependent upon time. So if we compose these two functions in this order and substitute the radius function in place of the volume input for the volume function, then we'll have a nice composed result that gives us the volume with respect to time. So the volume formula, our outer function, required 4/3 pi times something cubed. The something ended up being the expression 2/3 t cubed. We can simplify this. This 3 can distribute in because these two terms are separated by multiplication. If there was a plus sign there, we wouldn't dare distribute this exponent in. But we've got 4/3 pi times, well, 2 cubed is 8, 3 cubed is 27, times 8/27 t to the 9th power, and 4 times 8 is 32, 3 times 27 is 81, so we've got 81 pi t to the 9th power. The volume based on time is this equation. So again, this is particularly helpful if we need to know the answer to this problem. Say the question was asked, when will the balloon be full? Well, we might have a particular volume in mind, and I don't know how many cubic meters of air goes into a hot air balloon, but let's say it's 10,000 cubic meters, and that equals now the equation 32/81 pi t to the 9th. When we solve for t, our solution will be a value in measurement of time, and we would know exactly when the balloon would be full. The alternative would have been to solve for the volume in terms of the radius, and we would have to say something like this: the 10,000 cubic meter target is equal to 4/3 pi r cubed. We'd have to solve for some r value, and then with an r value, then we'd have to solve for 2/3 times t cubed. We would actually have to then solve even further for t. So rather than going through the process twice, we can simply solve a single equation one time now that it's written in composite form, and that's a big help. Here's another example. We're told that the number of cars that are produced by a certain factory in one day after t hours of operation is given by this formula between 0 and 10. So evidently the factory operates for 10 hours a day. Starting at time 0, we can plug in the number 0 and see how many cars have been produced. clearly 0. All the way up to 10, if we substitute 10 into this equation, we'll know how many, what number, or what amount of cars have been produced in that 10-hour period. Now, if the cost, C, of producing n number of cars is given to us with this equation, it certainly would be nice to know the cost to operate the factory based on the amount of time that it stays open. Maybe the factory only works 5 days a week, Monday through Friday, and is considering to open up another shift on Saturdays, maybe a half-day shift for 5 hours. It would be nice to know what the cost to operate the factory for an additional 5 hours would be, rather than trying to calculate the cost based on the number of cars. So here we go. We know that the cost based on the number of cars is equal to 15,000, I'm assuming dollars here, plus $8,000 per car, $8,000 times the number of cars. And we know that the number of cars that can be produced will be equal to 100 times t minus 5t squared. If our objective is to determine what the cost based on time is, which is again what we were asking for right here, then simply we would take the cost function that requires some n value, and the n value which requires the t value that we're after will be composed in this order. It's important not to switch these two. We don't want to place the cost function inside of the number of car function, because then that wouldn't really produce a result that we're after. We want the number of cars produced inside the cost function. So the cost function is 15,000 plus 8,000 times n times our argument, and our argument happens to be the entire n function now, 100t minus 5t squared. And so we have 15,000 plus 800,000 t minus 40,000 t squared. And this indeed is the cost based on the amount of time that the factory is open. So back to my question from a moment ago, if this company is considering operating the factory for an additional 5 days this week, well, we can evaluate cost of 5 at 15,000 plus 800,000 times 5 minus 40,000 times 5 squared, and we've got a result. Off camera, I calculated that to be $3,015,000. The alternative to this would have been to first calculate the number of cars that can be produced in 5 hours. And so we knew that that would be 100 times 5 minus 5 times 5 squared. And off screen I calculated that out to be 375. And then we can find the cost based on the number of cars, which in this case is the cost based on 375. And now we would need 15,000 times plus 8,000 times 375. So 15,000 plus 8,000 times 375. And we get the exact same result, 3,015,000. So again, the composed function saves us some time because we can establish the cost based on time rather than working through two intermediate steps. But also it helps us with problem solving too. So what if the company has $5 million that they're willing to invest for additional production? So they've got an extra $5 million for production, and they would like to know how much time the factory can stay open. Well, 15,000 plus 800,000 times x minus 40,000 times x squared, well, that produces an equation that we would then be able to solve. And actually, that's a bad example here because what we would be looking for is when does this function reach the cost of $5 million? And we were told that this function, this cost function, would only be good for time values between 0 and 10 hours. And if we look at the graph here between 0 and 10 hours, we see the cost function rise, rise, rise until we reach a peak. We can't use the cost function to the left of 0 or to the right of 10, but if you can see as I'm dragging my finger along this, this data point here, it appears that we max out at approximately $4.015 million. So there won't be a time within a 10-hour window that the factory would cost $5 million to operate. So let me just change the problem, and if we had $4 million, they've got $4 million to operate. Well, when does that happen? Well, that's an easy thing to solve. If we graph the equation y equals 4 million, we see the points of intersection occur here at 9.4 hours and again at 10.6. We would throw out this answer as extraneous because we can't operate for more than 10 hours. At least this formula doesn't work for more than 10 hours. But within the 10-hour window, 9.38 hours is the way to go. And again, the benefit to having this composed function is that we can answer that pretty quickly with one equation and one target value, as opposed to calculating intermediate steps. In this example, the volume of a cylinder, we know that the volume of a cylinder is dependent upon its radius and height. We're also told that the height, h, is always going to be 2 times the radius. Can we rewrite the volume function as a function of r only? Well, certainly. Now, in a sense, this volume function, v, is dependent upon 2 variables, r and h, and that's where pi times r squared h comes from. If we're supplied an r and an h, we could substitute those 2 components in. We're also told in this problem that the height can actually be determined based on the value of r. The height is always equal to 2 times r. So in this particular case, the volume based on r only could be obtained if we change this h value to 2r. And now we have pi times radius squared times 2r, and the volume based on r alone, since these two are alike one another, is simply 2 pi times radius cubed. So perhaps we're working for a company that builds these cylinders for some particular purpose, and every cylinder that they produce has to be the same proportions, where the height is twice the radius. And they've been asked to produce a cylinder whose volume is, say, 300 cubic centimeters. We now have a formula that can be used to identify the radius, or the width of that cylinder, or half width of that cylinder. So we now could solve that problem with one step, as opposed to requiring 2 intermediate steps along the way. In example 74, we're told about 2 different temperature conversions. The function c of f will take a temperature in Fahrenheit and convert it into degrees Celsius. Fahrenheit is our input, Celsius is our output. And additionally, we have another temperature conversion, kelvins. This will take the degree in Celsius to Kelvin. And our objective is to find a function that converts a temperature in degrees Fahrenheit directly to a temperature in kelvins. Now, this ought not to be too much of a challenge. Our end result is going to be Kelvin, so we would like to know the Kelvin conversion first, and that's Kelvin based on Celsius is Celsius plus 273. The Celsius temperature based on Fahrenheit is equal to 5/9 Fahrenheit minus 32. And now we can compose one with the other. We're going to take this Celsius composition and input it into our Kelvin formula, and we should be in pretty good shape. So Kelvin based on Celsius, which is based on Fahrenheit, would be equal to some Celsius value plus 273, or in other words, 5/9 Fahrenheit minus 32 plus 273. Depending on the level of precision in which this computation needs to be performed, it might be worthwhile to distribute the 5/9 into these two components and then combine like terms. So we'd have 5/9 Fahrenheit minus 160/9 plus 273, which would be 5/9 Fahrenheit plus, and this produces a pretty strange fraction, but that's 22/97. As a decimal, which is often what we're accustomed to working with, 5/9 is 0.5 repeating, so I'll use 4 decimals of that and round that 4th decimal to a 6. And this fraction is 255.2 repeating. And this simplified result takes our Fahrenheit values and converts them directly into Kelvin. Either one would work. Of course, this one with a little bit more precision. So all of this work was done in Part A. For Part B, suppose we need to determine 80 degrees Fahrenheit in kelvins. Well, here again, instead of computing Fahrenheit to Celsius and then taking that result and converting to Kelvin, we can go straight to the final answer. The number of kelvins that's equivalent to 80 degrees Fahrenheit would be 0.5556 times 80 plus 255.2222, and that is 299.6702 Kelvin. If we had used the other format with a precise answer, 5/9 times 80 plus 2297 over 9, we would get 899 thirds Kelvin, which is approximately 299.6 repeating. And of course, dependent upon your required precision, you might have one answer that is better than the other. Now, number 89 gets to be a bit of an interesting problem. We have a formula, d of r, that takes into account reaction time, and it computes the distance needed for a car to come to a complete stop when it's traveling r miles per hour. So in other words, if we know the rate of speed, we can substitute that rate into this equation, and we can then calculate the distance that it takes to stop. But what if we know the opposite? What if we know the distance and we would like to calculate the rate at which they were traveling? Well, in a single instance, we could set up an equation. Let's say that it took 200 feet for this car to stop. We could calculate the distance r. But if you're working in an investigative unit with the police department, you may have to do these calculations over and over and over again each day, and you don't necessarily want to set up a formula each time and solve for the unknown. It certainly would be nice to have a formula that does the work for you. And that's where our inverse equations come into play. Calculating the inverse function, or in other words, instead of the distance dependent on rate, we would like to switch these two and instead come up with the rate based on the distance. And that's what we're going to do in Part A. Express the speed or the rate that the car is traveling as a function of distance. Well, our original function was distance based on rate, and that was equal to 6.97 r minus 90.39. Now, in a similar approach to what we've been seeing earlier this week in finding inverses, we might want to change the letters from function notation. We'll say that d is equal to 6.97 r minus 90.39. And since we're going to go after an inverse, we need to switch r and d. Now, as soon as we make that switch, we're no longer talking about the same d value and the same r value, so just keep that in mind in the back of your mind that this new result is not indicative of the original. But our goal would then be to solve for this new value. In fact, now that I'm thinking about this, let's just use y and x. This might clarify some things. Y and x, just like we did before. Now we're switching x with y, and we're solving for the new y. So we have x plus 90.39 equals 6.97 y, and the new y by itself would be x plus 90.39 divided by 6.97. Now this new y is not the same as the original y. This one ended up being our inverse. The new y is our inverse. And if we think now back to the terminology that we were using originally, instead of d in terms of r, we now have r, the rate, in terms of d, our distance. So the rate required to stop a car based on the distance that it traveled before stopping would be x plus 90.39 divided by 6.97. Now the math wasn't too challenging, but it's still a good idea to verify that we did find inverses. So what I would like to do is compose one function with the other. And let's start with, let's say, this original function, d of r on the outside, with r of d on the inside. When we're done, we should be left with just the variable d. So we've got 6.97 times something minus 90.39. The something happens to be x plus 90.39 divided by 6.97, and I just realized my variables did not agree, so I need to change this to a d, and this x had to be changed back to a d. I forgot to make that switch when we were done. Following the order of operations, there's nothing inside of this grouping symbol that can be done, nor this division, so we will go ahead and distribute in. The 6.97 will cancel with this 6.97. And we're left with d plus 90.39 minus 90.39, and the two 90.39s will cancel, and we're left with d. So that's a good test. We should also investigate the opposite direction in order to be completely certain. So now r, based on the dr formula, should simplify in this case to r. And this formula did require a large fraction, so I'll give myself some room here. And we needed the distance, which from the original equation was 6.97 r minus 90.39 plus 90.39, all divided by 6.97. This fraction bar sort of acts like its own grouping symbol, so I'm going to look to the innermost grouping symbol and see if we can simplify there. Doesn't look like we can, so we'll move on. The negative 90.39 can be added with the other 90.39, and we now have 6.97r divided by 6.97. Those two will effectively cancel. They'll factor and reduce to r by itself, and that's exactly what we were after. When composing the two functions, we should end up with the original variable that we started with. Now that we've confirmed that these two functions really are inverses, we can actually use them as inverses and answer part C. Predict the speed at which the car was traveling if the distance required to stop was 300 feet. Now again, we could put 300 equals 6.97 R minus 90.39. That's going to require some algebra work in order to isolate and solve for R. But since we have the equation right here, we can say that the rate at which the vehicle was traveling based on 300 feet of stopping distance would be 300 plus 90.39 divided by 6.97. And here we have a single expression that can be plugged into a calculator to obtain a result, and no additional algebra is necessary. This comes out to be 56.0100, and I'm assuming we're talking about feet per second. Although, probably shouldn't assume. So feet per unit of time. And for the last example of this video, the function t of g, so taxes based on gross income, is equal to this expression. And this represents the income tax that is owed in dollars, t dollars, for a person who is single and has a gross income or adjusted gross income between $34,500 and $83,600. So question A, right at the beginning here, just wants us to verify that we understand when we're allowed to use this function, and it's asking this in terms of a mathematical domain. What is the domain of the function t? Well, as it turns out, any number can be used in this particular equation. There's no input that would produce a non-real result. However, in this scenario, the domain is going to be all x values that are an element of the set of numbers between $34,500 and $83,600. So if your income was below $34,500 or above $83,600, you would have to find a different function to use to calculate your taxes. And if we know the domain of the function, it would be a good idea to find the range of the function. Now, if we think about this for just a second, this is a linear function, and our instructions are kind of telling us that due to this being a linear function, it has a slope of 1/4, and it has some y-intercept that we would learn after distributing and combining like terms. But if we're looking at x values between $34,000 and $86,000, a linear function with a slope of 1/4 is going to look something like this. So again, we've established the domain for all x values in between these 2 points. For the range, we would want to know the y values between this point and this point. So when we're looking for the y values, what we really should do is calculate the lowest, or calculate the value at the lowest domain value, calculate the y value or y result at the largest domain value, and that will give us our range for y values. So let's go ahead and do that. For part B, we would say that t evaluated at 34,500 is going to give us our lower boundary for the range, and t evaluated at 83,600 is going to give us our boundary for the upper end of the range. Now, I trust that you're going to be using a calculator to do this math, so it's fine if you write down 4750 plus 0.25 times 34,500 minus 34,500. I'm going to slide this out of the way here. And in our upper boundary, we've got 4750 plus 0.25 times 8360, or 83,600 minus 34,500. And again, we're going to let the calculator do the math for us. And it looks like we get 4750 here because of the zeros. And we get 17,025 for this result here. So with those two calculations, we can now say that the range is going to be all y elements that are between the numbers 47, 50, and 17,025.